Good evening, everyone. Today is August the 9th, 2019. We just had a great long weekend civic holiday and enjoyable berry cottage trip. So welcome to another episode of my machine learning journey. Today I would like to talk about two things. So let's see what are the two things. So the first one here, I would like to share about my experiences in balancing between the upsampling folds versus the number of epochs to train for unbalanced dataset in deep learning models. So we can choose between whether we want to set the upsampling folds more or the number of epochs more. So this is what I find. We can set more number of epochs. If we do that, then it means that we are going to train the neural network at a deeper level. So it could probably catch more subtle pattern within the dataset. And it will generate more minority class prediction even when you are setting a very low upsampling scale. But whether these predicted minority class are false positives or true positives are up for an investigation. On the other hand, you can set a few epochs, so much less number of epochs to train the neural network, but you can upsample the minority class at a much larger scale. So in this case, you are training the model at a more shallower level. But it might still be able to produce quite a few minority class prediction. But again, whether this is mostly the false positives or true positives are still up for an investigation according to your target dataset. So this is what I find for my experience. And then the second thing I would like to talk about is the steps of the ULM fit pre-trained models in NLP Transfer Learning. So ULM fit is a set of framework invented by Jeremy Howard in San Francisco to train pre-trained models. So ULM fit stands for Universal Language Model Fine-Tuning for Text Classification. And this is a very good reference written by a few authors in German university, which I find very useful in understanding the little pieces in this ULM fit framework. So especially this is the workflow that they presented. So we can see that there are 3 steps. The first step is you download this pre-trained model, which is the highlighted in red here. And then after this pre-trained model, then you forward pass your data into this second step. So in this second step, you are using your own data to fine-tune the pre-trained model different layer weights of the encoder part, so which is the language model chunk. So after the second step, then you are further forward passing your own dataset into the third step. So in this third step, you are detaching the original decoder part of the pre-trained model, but attaching your own decoder, which is usually relevant to your target task. In most of the cases, it could be text classification or a name entity recognition. So on this graph, the decoder part of the third chunk is containing a ReLU activation function layer and a softmax activation layer. So in this third chunk, you are using your target data to fine-tune the classifier, so which is the decoder part of this model. So for today's section, I would like to go into details about this first step of the three components of the workflow. So the first step is to forward pass your data through the language model, which is the encoder part of the pre-trained model. So as we can see, for NLP task, usually it contains input layer and embedding layer for sure. So for input layer, we can see that it will generate a matrix. So this matrix, it represents the one-hot matrix. So what does that mean? The one-hot matrix, every row is a token in one sentence. So, but the column size dimension is actually the vocabulary size of your entire corpus, which contains all of the sentences. And after this one-hot encoded matrix generated from the input layer, then you will pass this one-hot matrix to the second embedding layer. So in this embedding layer, it has an embedding matrix. So the row size is the vocabulary size of your entire corpus, and then the column size is the number of embedding dimension that you want to embed every token. And in this case, so you want to use the one vector, which is having length of the embedding dimension to represent each word of your corpus. So after the embedding layer, then you will use the matrix multiplication to multiply the one-hot matrix with the embedding matrix. Then you generate this word embedding matrix, the third matrix that you see here. So this word embedding matrix, each row is is one token in your sentence. So I want to make a distinction here. So sentence versus the corpus. So a sentence is actually one case in your corpus. So it's one record in your corpus. So in this third matrix, every row is actually just one token in your sentence, but not corpus. But the column size is the embedding dimension. So now you completed the embedding part, so which you have generated word embeddings for your token. So you're using a vector with size, embedding dimension to represent each token. So after you generate this word embedding matrix, then you will pass it into the core encoder part of the pre-trained model. So in the default FastAI AWD LSTM model, you can see the core encoder here is actually 3 stacked LSTM layers. And in BERT model, pre-trained BERT model, then usually the core encoder composes of transformer-based encoder. So after you pass it through the core encoder, then you will again pass it into the decoder part of the pre-trained model. So we can see that in this pre-trained model, the decoder part contains a softmax activation layer. So this completes the forward pass of your target data through this pre-trained model. So then in the next section, we will explain then how do you use your own target data to fine-tune this pre-trained model, which is more relevant to your target data. Because we all know that the pre-trained model is usually generated on a really huge corpus. Usually the case is Wikipedia pages or the whole online Google News. That's how they use to generate word-to-vec embedding layer weights, and so on. So I hope that you find this useful. Please leave your comments and what you think. We will see you next time. Thanks.